Hello. By now you have learned how to complete the square in one variable or in one variable at a time. And now we will do a more difficult task, and this will be completing the square in two variables which are kind of interconnected. If you find this video too difficult, just remember where you can find it and go back to this video when you need it for more advanced courses like linear algebra and geometry 2 or calculus 3. Let's start. Completing the square in two variables. So our situation now is as follows. We will consider polynomials of second degree in two variables. So you see I have x and y, two variables, and you see that x is squared and y is squared, and here I have also a second degree term which is a product of our variables x and y. And these a numbers, these are simply constants, and the reason for numbering, why it is 1, 1 and a 2, 2 and a 1, 2, it will become clear in the next slide. So what is important here is that we only have second degree terms in this polynomial. We have only our variables squared and the product of our two variables and some constants before them. And the reason for numbering our constants is that they are usually taken from a matrix. And matrix, if you don't know matrices, think about 2 by 2 matrices as tables with numbers. And these numbers are numbered, you see. So this element here is indexed by 1, 1, and it means that it's in the first row and in the first column. This one is in the first row and in the second column. This one is in the second row and in the first column. And we want our matrices, by now, not always, in this particular situation, we want our matrix to be symmetric, which means that these two numbers must be equal to each other. And then you can produce a so-called quadratic form, which will be a result of matrix multiplication of our matrix with a column and row vector with our variables x and y. And if you don't know matrix multiplication, don't worry about it. I just tell you that it can be written in this way, exactly in the way you have seen in the previous slide. So A11 is this element, A22 is this element, and A12 and A21 are simply equal to each other. So this is why it's twice A12, just one of them. And it is multiplied by our variables x and y. And if you wonder how these quadratic forms are formed from matrices, you can look at the course Linear Algebra and Geometry 3. There you get everything explained. By now we are just happy with this explanation that we work with forms like this. And what are we supposed to do in this situation? We get a quadratic form in two variables, and we are supposed to rewrite this expression as the sum of two squares of independent variables s and t, and these variables s and t will depend on x and y in one way or another. You will see examples for this. And a and b are just some coefficients. And you will do this again by using this formula for square of sum or square of difference in a creative way. And if you don't want to be creative, I will show you a way which is like very strict and leads to an answer. By now I can tell you that this procedure can be described in a unique way, but it's not always in your advantage. So this is why I say it can, but well, usually I wouldn't advise to do this in forms in two variables. So if you don't want any creativity and if you just want to know the closed formula for this completing the square, you can read through this derivation. I will not read it for you. You can read it on your own. All the steps are here on the way. You recognize this one as completing the square, adding a square and at once subtracting the same number, so it's a zero operation, and then you end up in a situation where you have some constants times a variable in square plus some other constant times the second variable. So you see, this is our variable s from the previous slide, and this is our variable t from the previous slide. And as a resource to this video, you get a list of problems for completing the square in two variables. You can look at the first problem or first two problems, how I solved them, and try to do the rest of them on your own, so you get some practice here. And as the last part of this video, I would like to take this example in which I show you this particular form, how I can complete the square in two ways. So one way will be start at x variable and proceed, and the second one start with y variable. And so first method one, start with x. Start with x. So here I look at x variable, and where do I have it? Here and here. And I see that I have a coefficient 2 at x squared, so I can factor out this coefficient, and then I get x squared minus twice xy, right? Because 4 is also factored as 2 times minus 2. And I see that, well, I know what to do, right? If I add y squared, then I have a complete square. Think about x and y as a and b from our old formula for the square of sum. So what I have done here, I have actually added twice y squared. You see this? Twice y squared. So to be good, I have to subtract it, because I want my expression I'm producing now be equal to my original expression. And then I just have plus y squared from my original expression. And the only thing left to do is write this first expression in the parentheses as a perfect square. It is x minus y all squared. And these terms here are so-called similar terms, so they are both multiples of y squared. I have minus 2y squared plus 1y squared, which gives me minus y squared. And this is my first expression. I'm done with completing the square. I have written my quadratic form as some constant plus a variable squared plus some second constant times another variable squared. So if you want to compare this to this general expression, there you see that our a is equal to 2, our s is equal to x minus y, so this is this new variable which is squared. Then our b is equal to minus 1, because you have minus 1 times y squared, and our t from this here is equal to y. So you see, you have a, s, b, and t as in the general formula. Okay, I have to push this one down because I am about to start the solution with method 2. So method 2 will be start with y. Start with y. And I have to start with y, so I pick everything what has a y. And I see that I have y squared minus 4xy. And you see, to complete this to a perfect square, I have to add twice x squared. oh sorry, of course, 4x squared, because here you see I have twice y times 2x. So 2x is my second element from the sum, and I have to add this element squared in order to complete to a perfect square. And now, of course, I have to subtract it in order to keep a zero operation. And then I see that I still have twice x squared coming from the formula, right? And now I look at this expression here. It is already a perfect square. So this one is equal to y minus 2x all squared. Think about it. How do you square a difference? You take the first one squared. It is y squared. You have it here, right? Then you take minus twice the first times the second. So you will get minus 2 times y times 2x. It is exactly minus 4xy. And then you add the second one squared. It will be 2x all squared. It is 4x squared. So it is indeed our perfect square. And then I have these two elements which are similar terms. 2x squared minus 4x squared is minus 2x squared. And I'm done with completing the square in this with this second method. You see that it looks different, but it is the same expression, and you can verify it by just performing those multiplications. So in this particular case, if you now compare this to this general form, you get here you get a equal to 1 because you have no coefficient before the first square, right? This variable, this first variable s, is equal to y minus 2x. b is equal to minus 2, and t is equal to x. So you have a different representation as a completed square if you start with x and if you start with y. So in this way, this method, you have two different methods which lead to different representations of the same expression. And in the second part of this example 3, you have to use this quadratic form to show that you can have less than 2 squares in your answer, and to illustrate the term of independent variables. So what it means that these variables s and t must be independent. Well, if I look at this, I see at once that this is simply x plus y all squared, right? So you see that in this particular case, I get a equal to 1 if I compare to this one, s equal to x plus y, and then I get b equal to 0, and t, it does not matter, because if b is equal to 0, then t, it can be anything, so just forget it. You see that we just get 1 square, right? And now, in what way would I violate this requirement that the variables must be independent? Well, look at this. I could rewrite this expression in the following way. I could write that it is 3x plus y squared minus twice x plus y squared. It is true, it is the same expression, because 3 times something minus twice the same thing, it is just 1, this thing, right? So this is a true equality, but it is not good as a completed square, because my variables s and t are not independent. Even worse, they are simply the same variable. Both s and t would in this case be equal to x plus y. So I'm not allowed to do this in this way. If I just get a complete square from the first place, well, that's my answer. I cannot, I'm not allowed, well, I am allowed, but it wouldn't be good because it would lead to false conclusions about the topics which I usually would need this result for. That's all for now. Thank you for watching. Bye bye.